Okay guys, bit of a short one this. This is essentially, specifically for the synoptic exam, a little bit about chromatography and melting points, or specifically melting point ranges. So first of all, if we had our thin layer chromatography, and I have chemical A, chemical B, and a mixture of A and B, you're going to eventually end up with a solvent front, which is where your solvent soaks up to. Let's say that's somewhere around here. If you're asked to draw where chemical A will get to, you can't just guess and randomly put a spot. You need to figure out what the RF value is. So RF equals spot front over solvent front. They'll give you the solvent front. So you need to physically get your ruler out. This is why you need to bring a ruler to the exam and measure what your solvent front is. Assuming they give you the RF value, which they will, you can then rearrange this equation to figure out the spot front, which is the distance the spot moved. You then get your ruler out and very, very accurately measure how far this component will have moved. Let's say it ends up there. For chemical B, you would need to do exactly the same. Presumably, it would have a different RF value. Obviously, the solvent front would still be the same. And so you'd get a different spot front. And let's say it turns out the spot front of B is slightly higher. So somewhere around here. If we have a mixture of A and B, when they separate, you're going to end up with both spots. Look, this is B, and this is A. If I had chemical C, let's just extend this. If I had chemical C, and C was here, and my mixture was A, B, and C, I would also have a spot where C was, which would represent C. So if you have a mixture of different components, each component will give a spot where that component would usually be. Okay? Moving on, we've got our boiling points, sorry, our melting points. So the question in the mock said, if you have impurities, how will it affect the melting point range? And the key word there is range. So let's say here is our normal compound, let's say it's a salt, whatever, and let's say the melting point range of this is 150 to 160. Okay? We need to think about what effect on that melting point is going to happen if we add impurities. Well, there's two effects. First of all, if you add impurities represented by these smaller things, they could be smaller, they could be bigger, it's the same effect. By adding the impurities, what you're doing is you're messing up the bonding. You're screwing with the bonding. It won't work as well. And so if the bonding is weakened by these ions or whatever being different sizes, what effect is that going to have on the melting point? Well, it'll lower it. If you have weaker bonding, that will require less energy to break and a lower melting point. So if our pure compound was 150 to 160, our impure would have a lower melting point. And depending on how impure it was and how bad the impurities messed up the bonding would depend on how lower it went. But something else is going to happen as well. Not only will your melting point be lower, but the range of the melting point will be greater. Why is that? Well, because your impurities aren't messing up all of the bonding, only some bits. In our pure compound, all of these bonds are pretty much the same strength. So they're all going to break at pretty much the same energy, or pretty much the same temperature. If we look at our impure one, these bonding here, or kind of like round here, these aren't affected by the impurities. So these are going to have pretty much the same melting point as before. But this bit here, which has been affected by the impurities, that will have a significantly lower one. So what happens is when you have impurities, it lowers the melting point, and extends the range of the melting point. So you'd be talking something along the lines of, 140 to 155. Overall, it's lower, and we've extended the range a little bit.